Awesome stuff. So thanks for joining the Menti board already. There are even more people joining. So for the record, this is the Julia User Group Munich with a session on differential equations. And I'm really glad that all of you joined today to get an introduction to what's possible with Julia and this physics motivated field, but you can use it for all other things as well, like chemistry, bio stuff, system modeling, and of course also a lot of applied fields like in medicine or energy, power grids, and even many more. I'm not so much from the applied differential equation side, but there's so much research going on, and also in the application side. So it's one of the really nice things of Julia that it can combine these academic fields and communities, which especially in differential equations gave a lot and produce a lot of content, a lot of new methods and technologies, and make them readily available for you, for academics, but also applied data scientists and so far. Okay, so it's 5 parts. Let's start right into, but first one further question just to get a feeling for me. So thanks for giving your remark here, how you're coming here. So what do we have? A lot feeling good. Oof, yeah, I was expecting, of course, it's a long day as well. Monday we just started, so also some are tired. That's totally welcome. I'm the more thankful that you joined today, and also many enthusiastic. That's great. Feel good, optimistic, eager to learn. I hope there's something to learn for you. Also some nice plots and some nice visualizations. So also something for the eye, and a lot to just get to know. It's a super huge ecosystem, so we won't have time to go into everything. So my second question, just for me to get a little bit more feeling. So how your experience with this Julia world already? So because it's not super linear, this question, it's a bit from the left to right, increasing, but yeah. And in case you want to click multiple stuff, I gave you the choice to click 2 things. Okay. So that's nice. Looks a bit like a Gauss curve. Yeah. It's really cool tool. Thanks, Marco. Oh wow, we have already 2 experienced differential equations user. So I'm very glad that you are here today, and I would like to invite you to answer questions in case people ask questions. That would be of so much use. Thank you a lot for joining. But I fear that today I'm not giving any new insights which could help you, because it's really just introductory stuff to get a feeling of what's out there. But please feel welcome to just share your experience as well, and be there if people ask, or just share your insights. I'm also very happy that there are so many which are more, it's a little bit tilted to the left. So we have a bit more who are still new to Julia, and that's also the target audience. So it's more to get to know it, in this case to get to know the differential equations package. Awesome stuff. Okay, so last page, I've never used that, is that we have a question and answer board, but apparently it's not showing up. Okay, so that's then it. You can ask questions the whole time, but please don't use Mentimeter. Apparently it's not showing up here, so there's some little mistake going on, but all fine. So I invite you to ask the questions then directly in the chat here in Google Meet. That's kind of the best place, and then also others in the chat can answer the questions. So I've frozen video right now. Can you still hear me? Can someone give feedback whether I'm still here, Will?
I can hear you fine.
Perfect. Thanks a lot. Okay, so starting point for today is actually this repository. It was already in the invitation. So the first thing everyone has to do is to go to this repository, and you see it's just a little summary prepared for me, for you, and there are a couple of other introductions which we already went through, and today actually these 204 things have been added, which are giving 2 little introductions to the differential equations package. And yeah, we're going to start with the 01 introduction, of course, and let's hope we have time for also the stochastics part. It's actually not so much. So the thing you have to do is to click on this launch binder button here at the top. It's not always as good recognizable as a button, but indeed it's kind of a link which you can click, and then you get to this nice binder loading window. You see the preview, and within usually under a minute it should give you your own Jupyter environment. That's really nice. Thanks to the binder people and all the supporters, so thanks to Google Cloud, OVH, Jazz's Notebooks, and the Turing Institute. It's really lovely that we have these free resources, so every one of you has their own compute environment right now with the same setup, and you can experiment with it as you want. Keep in mind, this thing is going to shut down after kind of 15 minutes. And yeah, so it's a little bit encouraging to stay active, just execute a couple of stuff and yeah, try things out. But actually also if it breaks, no problem, just click again on the button, yeah, so come back to the repository and launch another binder and it should be there for you. Okay, so this should usually be fast, so for me it's still not there, and in case it takes too long for you, you can just click a second binder, because sometimes things happen, you know, and yeah, so it's having a cached repository in the back, a cached image, Docker image, which it's loading, so it should be relatively fast. Okay, so what we're going to look at today is the differential equations package, and this is one of the oldest package in the Julia ecosystem, so at least from my experience. I've been in the Julia, I've been more active in the Julia field since 3 years, I would say, and back then it was already the most famous package from all. And yeah, it just increased in number of size and depth, so it's by now the largest package about differential equations and really gives you access to state-of-the-art solvers, to the latest development, and also a lot of standard baseline solvers, so that you can do whatever you want in this field. So in the sense, and they describe it themselves actually, it's like a full stop solution. So if you look for differential equations, you can go here and you will find everything you need. So that's a little bit the promise. I myself haven't used it in as much depth to give you kind of the full guarantee that this is really the case. But from my experience with Julia, just using Julia as the language gives you actually quite a guarantee that this thing is hackable. In case something is not supported, it is relatively easy and straightforward to extend it to whatever you need in your own. So that's really a nice thing. And yeah, and you see here, so this is kind of the introductory field. There are a lot of things which are already supported in the differential equations package. So we have gone to standard ordinary differential equations. We have partitioned, we have stochastic, we have random, we have differential, algebraic equations, delayed, we have neural differential equations, and yeah, also combinations of these. And there's even support for discrete differential equations with this. So here's the mixed, discrete, and continuous equations. So this thing is really super powerful also in terms of optimization, but more focused on the continuous systems. Okay, so this is a little bit surprising. So mine is still not there. So I hope that for you that you have. Hi Christoph, glad you joined. Thanks a lot. I hope you have the a running binder version right now. So I'm a little bit surprised. Mine is not starting. Let's give it a second run. So yeah, now I just clicked again on it and it started within 5 seconds. Okay, so I hope every one of you has this Jupyter notebook. I make it a little bit larger. So there are other introductions which we went through in the user group, the Julia User Group Munich, but today it's the 04, the differential equations introduction, which we want to look at first. So you just need to control click on it or just click on it. And so I made control click to have the other window still open. And then you should have access to just a Jupyter notebook. So who's not familiar with the Jupyter notebook, the most important thing is that you have a run button here with which you can actually execute the single cells. And you have a plus button here, so with which you can create a new cell. So a cell is kind of like a text editor. And you have many text editors here, and if you have such a Julia or just a programming cell, you can actually use it, and it's really just normal Julia. And I'm still connecting to the kernel right now, so hence I don't see any output. Now I'm connected, so it should execute in a second, and you have just standard Julia surroundings. So you can also import packages. And another way of executing things is, which I use most of the time, is Shift Enter or Control Enter. But you can always kind of just just add a new cell and run it. So that's the totally GUI way to do it, and it works. So you've kind of a ready setup, So you have a Jupyter notebook here running on the server with a lot of packages pre-installed and actually also pre-compiled, and so that things should be a bit faster. So that's really nice, and powered by Binder. So that's thanks to that. Okay, so the differential equations package has a lot to do, and the first thing which the documentation really recommends is to go through the tutorial about ordinary differential equations. So that's the first thing everyone should have seen, and hence I just rephrased this tutorial into a Jupyter notebook for you so that you can really execute it right now. But just for you to have the background, so we are kind of having a version of this first tutorial, the ordinary differential equations tutorial. Let's make this also a bit bigger. So this is now kind of recompiled into a Jupyter notebook version, which we have here, so you can a little bit more conveniently go through it. So let's jump right into it, but again, maybe a little quick check. So can everyone hear me good enough? So just important that the feeling is kind of nice, that the internet connection is working. Nice, thanks Alice, thanks Marco. Okay, perfect. That's enough. So let's look into it to give you already feeling. And maybe go all to the first Julia cell here, and you can click also on this little run button to run it, because the first time a Julia package loads, still some things take a little bit longer, because Julia is a just-in-time compiled language. We have pre-compilation, which improves startup times, but still there's a couple of things which just need to be compiled on the first run. And then they are blazingly fast, but the first time takes a bit longer. So what do we have here? We have kind of just an introduction to a general differential equation. So we have our target variable u, where we don't know the real formula, the equation, but we can model the derivative of this function. So that's kind of the usual approach. The real thing is a bit too complex, but we know how things change over time. So this is kind of really general approach, and you can use it to model anything like this. Yeah, super successful in physics and everywhere. But this is the general approach. So what do we have here in addition? What do we get? We define kind of our function, how things change over time, and we get as input parameters the actual values themselves. So how's the world at the time where we currently are? And in addition, we have kind of also access to some parameters. This is just for convenience, so that we can make things a little bit more general and then change just some parameters and then look at different versions of things. And the last thing which we also get is the actual time where we are in. So because we model the difference over time, how things change, it can be quite important, like what's the current time. And to begin with, we have just a very simple example that things change in a, yeah, what's this? Yeah, like an exponential manner. Yeah. So if we have the change over time is linear, so alpha is just a constant, linear to our current value, what we currently have. So if we solve this, we know that this is actually exponential function, and yeah, because we add what we already have, this gets exponential. I think it gives kind of an intuition. And how do we do this in Julia is now kind of the interesting part. So we define our function really plainly as a Julia function. So first is you import a package using differential equations. If you're new to Julia, you may be confused because there are two versions to import a package. There's the import and the using. And the using is for practical usage like an import, but it in addition brings a couple of variables into your current namespace so that you can just start and use the methods defined here. And you see that we do this right now. So we have an ordinary differential equation problem, and we have a method solve, which comes from the package. And yeah, so what we first do, and this is really nice, neat Julia syntax to define functions. We just define a function called f, which gets u, p, and t as parameters, and we use a simple equal sign to assign this to an expression, which now just has a constant 1.10 as this alpha value and multiplies it by the current value of the system. So you see that this assumes that the system now is just a single value, which you can multiply directly. We have a u0, which is like our initial world, which we start with. We start at 1/2 now for this little example, and we want to simulate our system for a time span between 0 and 1. So this we can now put into a differential equation problem by first providing the function, the starting value then, and then the time span. So this you just have to remember, but it's relatively straightforward. So you pass them by position. Yeah, first it's first and second and third. But yeah, it's the usual way, and defining them or giving them names first is one of the very straightforward ways to make it very clean also from the code side, so that you see what's going on. And yeah, and finally we call the solve function, which is provided by the package, and we solve our problem with a specific solver. So this is kind of an art in itself to choose the right solver. Here we just take the example from the code. So the SID5 is one of the recommended options, but you can check out the documentation there. Yeah, there's a little art to it, but you have also just a standard recommendation. We have a relative tolerance, which we can set here, absolute tolerance, and this is just to give you an idea that there are really a lot of more parameters which you can adapt. So this solve is like the general entry point where you can specify a lot of things. Same for the problem itself, so you can specify further things for the problem. So you see that if we computed this, we get a solution which here prints relatively nicely. So we see that things have been successful. We have a time vector for which we computed our system, and we have our solution U, which is then our system for this time. And we get a nice little visualization of this using the general plots package. So plots is the user package for plotting. There are some other packages out there which are getting also more momentum. So the Makey project is really awesome, but yeah, the plots is still for newcomers, is the go-to, and it's also used everywhere. You see it's relatively simple. So what we do here is just we activate again the plots package, and this thing, I should have made a comment here, is just to get a nice interactive plotting system in our Jupyter notebook. So this activates Plotly backend. So you can visualize plots different ways. You just can render them as PNGs, as images, or you can render them as nice interactive HTML, JavaScript combinations. And this is what we do with the help of Plotly. So then we can just use the general plot command with our solution here as the first argument, and then again with thousands of parameters you can tweak whatever you want. So here we tweak the most obvious stuff, the axis names and title and also some label. And nice thing, you can adapt, you can add to an existing plot, and the only difference is that you provide an exclamation mark in the end. So this is the Julia sign for changing stuff. So we are going to change the current plot and add a new thing to it. And what we add is here the time itself. And over the time we plot a function. And as you recognize, this is our function, which is the optimal solution. So if we solve our system, this is the true solution. And we just plot it here as well for visualization purposes. So for a couple of you, probably this already compiled. And this is one of the biggest drawbacks of Julia, which is currently also approached. So people are working on this, but because of this focus on being both high level, interactive and super performant with focus on throughput, we have this compilation step in the beginning. So in Python you would see the first plot a little bit faster because it focuses on just executing the code on the fly, on interpreting it in the sense. In Julia there are additional steps happening to make the code fast, and these additional steps are just slowing things down on the first time, which is a little bit unfortunate in this setting. But from the practical perspective, it was never a real issue for me, because as soon as you have this thing running, it's really blazingly fast. So first, enjoy the nice interactive Plotly landscape. Yeah, so we can zoom in, we can zoom out, we see a focus, and we see also that we found the right solution. And just to give you the idea, so if you execute it again, it's now much faster. So it doesn't take so long again and should give you a plot in reasonable time. So you see it's already there. So it's really only the first time you plot things which takes the most time. Okay, so we have a couple of questions. Roland asked how the time is chosen. So this depends on your modeling. So time is of course like continuously going on. So you can kind of put everything into 0 and 1. But if you have a precise timing, which let's say you want to model the last 2 years of 2 populations in an ecosystem, how they evolved, of course it would be a natural thing to use this time frame and map it there. Still, you probably would map it to real numbers, to have a better feeling, to make it a bit more appropriate for the system. But nevertheless, you give an interpretation, then 0 would be kind of start 2016, and 1 would be end 2018. That's really more based on your concrete use case. Marco asked question what is meant with interpolation, specialized fourth order free interpolation. Yeah, we have this as an output here. So yeah, we see this in a second. At least this is my understanding of it. So we can access the solution in two ways. The one is just by accessing the single elements of these lists, of these arrays. So that's quite natural. In Julia, we can index into things by using the brackets, the square brackets, and the first entry is actually the 1. So you may have recognized this already. But yeah, we actually start with 1 and then count further. And we can also use just the call syntax. So we see we have our solution here, and now we use normal parentheses. And this will use the interpolation. And here the interpolation can change depending on the solver you use and a couple of parameters. You specify configuration, and giving our configuration, we get an interpolation which is actually not just linear, adding two things and taking the middle of it, but we have a fourth order interpolation, which is just more concrete. And we get it, so I interpret we get it for free, like it was not in addition that computed, but just the process itself had to compute it anyway. So we can safely use it and don't fear that anything was way slower, because we now have this awesome interpolation. So this works nicely, and you can also check it, like here they use an index, and here you use the precise time. So if we go something near 0, yeah, so we approach, what do we approach? Yeah, 0.5, yeah, it's the value, time 0 matched to 0.5. So it should be more nearer 0.5. Let's get this there, and it is. Okay, so what do we have? Thanks, Christoph, for actually also answering the questions. Wow, that's even much better. So just to repeat what Christoph already answered in the chat, the free stands for that it's not, yeah, it's all done with just dot products. So actually linear combination of the basis functions are enough to get the fourth order interpolation. P, we're going to Pablo, asked where the parameter P comes from. It's given by the system. We are going to look into it next. Yeah, we will have an example for it. Okay, great. So now we have a couple of interdependent systems. So we will see this function again. That's the Lorentz attractor, one of the most famous simple examples for differential equations and the dynamic system. So we have three interlinked functions, equations for x, y, and z. So this is actually a nice example also to get 3D plotting in your browser. And we can define them more or less directly. So you see now that instead of having a single variable, in this system here, we assume now our world, our u, is a vector of 3 values. And what we do now is we use a in-place version of the update. So let's take a first single look back. So this style we used before was that we define a function which just gets our world and our current time parameters and returns the change. Yeah, so this is the standard system. However, in terms of computation, it sometimes saves a lot of performance, a lot of computation to do this in place. So here we have actually du as the first parameter. So this is our difference, how the system changes over time, and we are changing it in place. So this is itself a vector, and we are overwriting the single places with our solutions. So we're not returning these three equations as one vector, but to save some allocations, we are writing this directly here. And we notify this also in our function name, it's good practice, and so that we add our exclamation mark at the end of the function. Okay, so let's define this. You probably already run it, and we can again just create this. So what we need to provide again is an initial value. Our initial word is now a little vector, so we can execute this also separately. So you see with this semicolon, you name that it should be a column vector, and we also provide our time span, which is now a bit larger. So this system is defined apparently that you see it evolving like for 100. And if you run this, so we again define our problem now by specifying our function, it will automatically recognize that you use the Inplace version. So it looks like what is defined for it, and it sees that this function uses 4 arguments, and this way it knows, okay, it's following the Inplace convention. And yeah, so we have our start value and our time span, and again, and this we can solve directly. So now we use a little magic here, and this is really kind of good for you to remember in case you just want things done. Yeah, there's an automated way to pick the right solver for you. Of course, this can always be improved manually, as everything automated is usually a heuristic behind it, but it's really nice for just getting things tested and tried out, so you can solve this directly. So this takes a little bit of time, and we have now again our plot, and we specify one extra argument here. It's a special attribute for this plot command, and it specifies that we want to print the first variable, so it's x against the time, and we want to print the y against the time and z against the time. And having this actually gives us a 3D plot. So the default plot version is a little bit different, stacks things together, but if we specify this explicitly here, which is not much, we can get a nice 3D plot. So I guess a couple of you already have it, and I really love this. This is super awesome about Julia to have this integration. So for me, it's now coming, and this is powered by Plotly, of course. So also big thank you to the Plotly team for making this possible. So this is not an image, but this is an interactive 3D plot, and it's so awesome that you can really zoom into it and have the feeling of interactive stuff. So let's zoom a bit into it to see that this also works. A really nice Lorentz attractor. And of course, this is just a bit of a toy example, but this interactive feeling is really helpful if you're a data scientist and exploring data, because then you can just zoom wherever you need to zoom into and have the details you need, and don't need to re-execute your plots for just zooming. So I'm a super fan of this interactiveness. So now let's take a look at the question. So we have also a P0, an initialization for our parameters. This is really now coming. So we are now looking into parameterized functions. Yes. Okay, so now we have a parameterized Lorentz version where we just use the parameters. And this is now another version just to define the function. So you've seen that we actually have vectors which we can use, but you can give them names, of course. So here we have our outer word, which is a vector, and we can use argument splatting to have them named x, y, and z. And we do the same now for the parameters. So we again have a parameter vector, and we call them sigma, rho, and beta. And we now overwrite again our final du, our derivative, but we can actually use double equal sign to also give the derivative a nice name, just for, it's visually more appealing, but it also can improve just maintenance of your code. So having a name for something definitely improves maintenance and debuggability. So if you kind of like this, really feel motivated to give things nice names. So here we have our system again defined. Now we replaced our hard-coded values with respective parameters, and we just add them now from the outside. So in addition, we specify our parameter vector, and we hand over our parameter vector as the fourth argument. It's really just like at the end of everything, and this will be passed directly into it. We can solve the system again and plot it again, and now things should be much faster because we plotted this already. And yeah, and you see there's the same here because we use the same parameters. So feel free to just adapt these parameters a little bit. So this is the purpose of parameterizing thing, that it's simpler to actually try different versions of it and see how the system behaves. There's also ways to do this interactive. I haven't included an example right now, but Julia also comes with support for interactive widgets. If we have time in the end, we can take a look at it, which then would simplify this changing parameters and having, executing a new plot. So that's also a nice thing. But as things are compiled, probably you should. It's taking a little bit longer now, I'm not sure. Probably the system just needs some computational resources. And bear with us, we have free resources, but they are of course not super powerful. So again, the same Lorentz attractor, but now parameterized, so that you get the feeling it's just simpler to work with it. So this really can matter to try out different things and in your interactive workflow. So what's left for this part? I've still two examples here, and the first one is a non-homogeneous equation. So we are now modeling a pendulum, and what we are doing here is that let's take a look at the formulas again. So we are modeling a pendulum with two variables. So the first theta here is modeling the angle of the pendulum, so how far it's to the side, and we model the difference, the derivative of this angle with our omega, which is in the sense the rate, the change rate. It's called here angular rate of the pendulum. And this one, so this rate, this velocity, is modeled a little bit more complicated. So it has a negative factor which takes the gravitational constant and the length of the pendulum, and includes also where it's currently where its angle, and takes this negative so that things go again to the ground. So we have a gravitational force working here, and it's because of a minus, it's relative to the length. The more length we have, the larger it is probably. I'm sorry, maybe someone else has a bit more knowledge why it's precisely this way, but I think the intuition is kind of the thing. And we have a second term which now has an m here, and in the text it's also specified this big M is now an external torque. So an external force applied to the system, and this is positive, but it has the mass of our pendulum and the length squared in the denominator. So the higher the mass, the less force we have. So this is just modeling inertia. And with this together, we have kind of a nice modeling of a pendulum. And let's get this into code. So we have just some constants which we define. So we have length 1, mass 1, and our Earth gravitation, and we define our pendulum functions now. Again, making it a bit nicer, we can give it names and get the functions more or less directly in here. So we need to have an initial system, so that's also nice to see. So in Julia you not only have this UTF-8 characters you've seen a lot, but there are also other UTF-8 characters which you can use for the subscript. So we have seen the 0 just putting after it, but you can even make it nicer looking with the subscript 0. So that's nice. So this both together give our initial state. We have our function actually, so we see that this external force is a function of time also in our formula, and we can just make it an anonymous function of time. So this works directly. So you see a couple of Julia nice quirks here. So we have a number directly in front of a function, so this works. In other languages you have kind of this multiplication sign, and we've also already seen it above here, so 3g, which simplifies the syntax. And this we haven't seen so far. This is a way of defining an anonymous function, but we could probably also, I haven't tested this, define it this way. There may be a reason to not define it this way actually. Let's see whether it works. And yeah, finally we solve it again. And you see here, now we have the m as our parameter, and it really doesn't matter so much. Yeah, before we had a vector which we pass as a parameter. Now we pass a function as the parameter. It all works. Yeah, so with the function, of course, we have the most flexibility. So this way here we get the time dependency in the function. And actually now this example uses all parameters. Yeah, so that's the others haven't used the parameters itself and also haven't used t. So this is in this sense nice to also make use of the current time actually by calling our parameter with it. So you could name this m if you're kind of familiar, but it may kind of confuse because the standard is to have a p here. So because following the standard convention, you have a p here and you could kind of name it also m here. So that way would look even a bit nicer. Okay, so seen after end of expression, so sorry for confusing the syntax. You are not allowed to place an empty space between the number and the function call or the variable. Okay, so and this should give you our solution to our two variables, so the angle and the force, the velocity, so how the angle is changing. And yeah, so you can kind of play a little bit with it, and the thing which you can play, of course, here is the external force. So you can see how the system behaves if we just change the force a little bit. Yeah, so let's increase this kind of by a factor of 10, and probably this doesn't do much. Yeah, it's a pity that we lose the last plot by re-executing. You can just copy and paste it to another cell and see it working. So probably this just scales. Yeah, roughly. So, but we can also go to cosine. So you can really do whatever you want. You can go to exponential. That might look even a bit more different. And yeah, so you can really try out things and have the feeling that this is all under control. There's no special thing going on here. It's really just Julia code, and you can do whatever you want. So this is one of the niceties I really like and appreciate about Julia, that everything is first class. So it's not like you have to comply now with the differential equation package and only use functions which are working in the differential equations package, but this is really all Julia you can use. So a bit more to the details. There are things if you then use solvers which take automated derivatives, then your code needs to be able to be automated to take automated derivatives. Yeah, so this is totally different now with the exponential as expected. And not any longer a pendulum. Like, yeah, it's not pendling. Yeah, but also there. So the realm of supported Julia functions is really super wide, and this is only for the special case of automated derivatives, which is already a super powerful feature, which is in other languages not easily possible, but you need to go back to a sub-language in the language. Like in Python, if you have the deep learning frameworks, yeah, they have their own subsystem where they actually can use auto-differentiation. and here we just use Julia. Okay, so we saw quite some power already. And last example now is that you see that this thing is also flexible in the things which you put into it. So we already saw a world with just a single value, which we started in the beginning. We had a world with 3 parameters for the Lorentz system, which had the 3D modeling, and we had now this pendulum, which had 2, let's say, 2 parameters, 2 dimensions. And we can also put kind of other things than scalars and vectors. And here we put a matrix. So this is another nice way in Julia to write matrices. And just to get it right. So what it does here is that the space is actually concatenating column-wise. So you have a row vector in the end. And a line break is really like a semicolon in the previous example, which then concatenates the rows and then builds up the columns by it. So it's super intuitive, and I appreciate that this is possible. So we have now a matrix which we put on top of an initial matrix, which we just changed by matrix multiplication. So how our system changes over time is really just defined by this matrix multiplication, and we put this into our problem, and we see that this just works. And the thing here is that everything works which has a linear index. So you need to be a little bit careful. Of course, you need to support it. But many things are supported and work quite nicely. And this is one of the nice things of Julia, which I can't go into detail today much, but the power feature of Julia which enables this is called multiple dispatch. Let's solve this matrix problem for now, so that let's see that this actually also is solvable. Just to give a little bit background on how this actually works, it's really so if we have a function and we can define it for some values. We can, for example, add stuff together, and if we call it, we successfully added some stuff. And the nice Julia feature, and this is really the thing which glues everything together, is called multiple dispatch, that we can be a bit more specific. So we can say that integers will have a specific implementation, like going to how they are realized and having a more efficient implementation of how you add them. For illustration purposes, we can just do something completely different. Of course, this is not useful, but you get the point. So I'm still waiting for my plot to show up. This is why I don't see the outputs. But I hope the plot is there in a second. Yeah, there's the plot. And then you see also my output. So I start with a function, and it's generically defined. So it works with just a 3. Now I specialized it to my integers. I have a 1 and 2, and it takes the specific way. And the really cool thing now, and this is how this whole system works so nicely. So if I now use something else than integers, like floats, I really get the other way of doing it. And this is super generic, so I can also define strings with it. Maybe let's take a first look what it means to add 2 strings. Because in Python this would work. In Julia this does not work. Because it's actually not defined for strings plus. So what you would expect to work is actually it's defined with the multiplication sign, and now we can actually just concatenate our 2 strings, and it will work. So this is the multiple dispatch behind the scene, just for those totally new to the system. This works for arbitrary many arguments and for all combinations. So you can also get abstract. You can have kind of a number which is a supertype of all numbers, and you can also kind of leave it out at 1, which is then kind of defaulting to it can be anything, and you can combine this as wild as you want, and it usually makes kind of sense. It's a very intuitive way to define generic stuff and let it open for specialization. and for later addition. So it's an open world in the sense you can always later on extend your functions. And this way, all this, what is here behind the scene, or what we used here to do this calculations, you can actually also define your own types and extend it. Because, yeah, everything is open by using the Julia language. Of course, you need to be a bit careful in the design, but they have been, so you can freely assume that you can easily extend it. So what we see here is actually 8 different systems, and these are the 8, of course, of our matrix. And that happens to be because our matrix has a linear index as well, so it can also number the entries from 1 to 8. And now a nice thing is that we can also access this. Okay, so this is actually not so important, just that you can see we can also again define a faster way of doing this by using the Inplace version, and there's an Inplace multiplication function in Julia which can speed up multiplication, matrix multiplication. So this is just the very same, but that you've seen it, that you can also define the Inplace version. Yeah, okay, before seeing kind of how we can actually index in this, there's one extra nice thing to see this dispatch working, and this is that we not only have this one array in Julia, but there are many arrays. The default one is super flexible and will be a good fallback for many of your usages, but here there's one example for having a static array. So this is just something which you cannot change afterwards. That's for its main named static, and it can actually speed up things quite a bit because you don't need to allocate places in memory, or at least not so many. I'm not 100% sure about the details. You see the plot is again the same, we expected that. But it can speed up things quite a bit, especially if you reuse the array a lot of times. And also from a from a software engineering perspective, it's also nice if you want to reason about your system that things just stay constant, unchangeable. Yeah, it's called immutable. So we define the very same, but just put our little S matrix macro in front to change things. And what's now important, I come across this when bringing this to Jupyter, is you cannot use the same function as before, because you see we overloaded the function. So I needed to name this function slightly different. So here I had put it f prime, because the problem will choose which kind to solve by inspecting the function. If it sees this 4-argument version, it will actually try the mutation. So we can give it a try. Let's first see that this actually works. So we have now a completely different type. So this is a static array. Maybe we can also take a look into it. So we put different things in it, and it still works like the normal way. It's not mutable any longer. Normal arrays are mutable, this is not, but the standard solve implementation does not need this here, and so it can work it can work directly. And we will see a similar plot. So this is really nice, and yeah, gives you the guarantee that whatever requirements you have, like if you really need to tweak performances for your system because you go so large scale and have a specific problem, you can really tweak it. So this is one way we change kind of the matrix type. So this is an S matrix, yeah, and if we just a static matrix, and if we just have a normal vector, we see that it's really an array, or maybe it actually presents itself as a vector, but still another type, right? So it's a matrix, a normal matrix, but it's not a static matrix. It's really different type. So for other systems, this is quite hard to actually support both of them. And you see also that they are parameterized, so you can also switch to float 8 if this improves your performance, yeah, and if you don't need the accuracy. So this is really whole tweakable, and one of the reasons why Julia was probably invented this way, to really make it possible to afterwards specialize your system in a way you need it. Sorry. So floating points is definitely one of the intuitive ways. So if you use less bytes to represent your numbers, you can save quite a lot of time, but of course you lose precision. And the case goes also the other way around, so you can have infinite precision numbers, which just increase the bytes representation by a flexible layout. And this works as well. So if you don't need the performance, but you just need the precision, you can tweak your system also in that direction. Okay, so we see that it solves again the same system. And now just to give you the idea, so I can use my predefined f, and this will actually not work, and it's nice to see, because we defined f already with the in-place operation, and it will just assume that it can also use this function on our static, but it does not, because it's static, it's immutable, and we will get an error that it's not, you cannot use setIndex. And it will need some time apparently to get to the error, but there we are. So it says that setIndex is not defined. Yeah, so mutating does not work. And we can inspect this by using the methods function, which will show us that f indeed has these two functions defined. And this one is apparently kind of enough to trigger that it uses another implementation. So just naming it differently, don't know, yeah, solves the problem. Because it defines a new function, and then that's fine. Okay, so time for some questions. What do we have here? Okay, thanks, Philip, for asking the question. Maybe I'm a bit... Okay, so we have a lot of comments already, which I missed. Okay, nice. Thank you all for helping out here, also in the chat. This is always very helpful. Yeah, so just in case you wonder what tutorials are there, there's really a lot of tutorials out there. I will give you the links also in the end, but the support is super extent. Sorry, let me get a drink. Okay, the Greek letters are already there, so you have LaTeX completion. Thanks Pramod for helping out here. Yeah. Okay, so we have a couple of comments about the syntax. Yeah, thanks also Christoph for the performance details, when to use static arrays and when to use the mutated versions, the mutatable versions. In case, of course, it's always a good idea to do the benchmarking. Yeah, so these things can be quite complex systems, so it's always nice to do some benchmarking and some profiling to get a good understanding of the system and just see how it works. So last part of this one is that because it's a matrix now, you may wonder how the solution actually looks like. And we can again access our solution kind of at specific time points, getting them at the index. So remember how our solution looked like. So we have again our time and our u, and yeah, so let's hope we get the solution, and we can see that it now returns kind of whole matrices for each index. Yeah, we see them actually also nicely here. So u is a vector of these matrices. We can access them directly. But there's actually a bit more support to it. So we can also access the precise value of our matrix. And this is just to not get confused, that you've seen the syntax. And yeah, you can also use it kind of as a convenient syntax. So this means that we access now the fifth element of the matrix at our time index 3. And instead of using the linear index, which can be a little bit unintuitive, especially with such hard-coded situations, you can also have two versions in front, and then you get kind of the matrix index defined by these two indices. So let's first kind of change this. So if you do this to a column, actually the effect is that you get the whole time series. So this is like, I think it's the same symbol actually in Python. So you get a vector which is the whole time, and now the fifth element of the matrix. And here it's kind of the 2 and 1 element of the matrix, which is another one. And I just added to you here the way you can get from the one representation to the other. And this is the Cartesian index and the linear index. And this way we can see that if we want to check, so the 5 should equal actually to 1, 2. So, and this should now be the very same, and it very much looks like the very same. And we can also do it the other way around, of course. This is just to give you the real feeling. This is just convenience index, convenient way to index stuff. You may want to use it, and it's quite nice. Okay, so that was the little introduction which everyone should have seen if they want to start with differential equations. So big thanks, of course, to the differential equations team for providing the original tutorial in the first place. So this is really nice to have a common ground for everyone to start. And I find it also very well done. I changed a little bit here and there, but not much. And yeah, so it's really nice, and you see this also in the documentation. There's much more to it. Yeah, so if we have a lot of links here provided, which you can check out later. And it also mentions that the documentation itself has kind of 3 main scopes, which is important for you to see. There's a tutorials section with a couple of examples, which are a little bit more quick start, go through, but going into deeper details. We have a basic overview about just functionalities. We have the problem type section, where you have all these different problems which you can solve with differential equations. And we have also the solver algorithm sections, where you can look into the different solvers which are available and how to choose also the correct solver. And yeah, you see there's even more. There are additional features, analysis tools. So this whole ecosystem is really nice. We have a domain modeling section where you get applied stuff. So we have physical models, financial models, chemical things, and we have a lot of more. And one of the main links also, so let me also share this link in the chat right now. So this is the tutorial, and this is a link which is also mentioned several times in the documentation, where you have a lot of more tutorials. So this is the collection of tutorials about the differential equations. So actually the name is a little bit more general. So there's scientific machine learning community which built around the differential equation package, and there's many things. So this is the table of contents. It says also how you can try them out. So we have introduction stuff, we have exercise, we have modeling examples in the different fields. Here also, just to mention, because we haven't seen this before, some bio examples from biology. Here neural systems, neurosciences, that's where I'm from actually. So also really nice. And yeah, a couple of advanced features. And also differential equations uncertainty. So you can check it out. There are a couple of more tutorials which are very fruitful and may just fit exactly your use case. So it's always nice to have the overview, what's already provided. Okay, so little check back, time for questions. I will also go back to the notebook, but let's check the chat again. Okay. I use set field myself. was developed in Freiburg. So we already had a talk about it in the meetup in the Julia User Group Munich. Quite nice. Sphinx for Julia. So Sphinx, so the one question from Sviatoslav is whether there's a Sphinx for Julia. Yeah, and it already was answered by Krishna, and I think it's the same. Yeah, that this actually is a question for documentation, and all this documentation you've also seen is actually built with Documenter.jl, which is also referred by Krishna. Thanks a lot. And yeah, so that's quite nice and handy, and you have a lot of documentation support, which helps you just reusing your documentation. So if you document your functions, you can easily reuse also this in the document in the final docs, like you have it with Sphinx. So this support is there. So what is the timing? We are already a bit more than 1 hour. So what I wanted to show you also. So please raise your questions. Feel free also to just ask with your voice, but also in the chat. The other little tutorial which I put here is a compilation of the stochastic differential equations version. And that's because I actually have some background in the stochastic systems. So I studied applied stochastics back in my master's, and hence I really like the systems quite a lot. So I've looked into the stochastic differential equations from the math side, which is quite heavy, and I'm very happy to see them being able to apply just right away. There are different ways how to get probability into such time-dependent systems. And the stochastic differential equations, they are usually written this way, that so my system just failed. So I need to reconnect. So we have kind of an additional component now. You remember that in the very beginning we had that du divided by dt, so how the system changes over time is modeled by our function. So let's have this directly here. Yeah, so this was where we started, the very simple thing. And now our extra is that we put the dt on the other side, like mathematical trick if you want, but it has a valid mathematical definition under the hood. And we add another term, which we call g, but same parameters, and where we differentiate according to a capital W, and this is a so-called Wiener process, a Gaussian process, and it defines our probability, our uncertainty over time, our randomness over time. So the Gaussian process is like one of the normal, or the Wiener process is one of the really standard things. I just have a wiki page open here, so you see kind of a little example image here. That was a bit too much, and it's really just noise in a sense, but defined well over time. So if a couple of things, you see that this is really a time series which is continuous in that sense. You get this in multiple dimensions. Just to get you a feeling, these are the 4 properties of this process. It starts at 0, not super interesting, but then it has a property called independent increments, so that you can't conclude from what you see currently to the past. And the increments are Gaussian, and everything is continuous. So that's it, and with this you already fully define the process, and this is one of the standard processes in stochastic processes. You have many things on top which are defined there. So I'm now switching to my new system, just because I mentioned that it broke down. And yeah, so we have now a second function which is differentiated over this Gaussian process. And we have got a bit more specific implementation here. So If we again use this exponential version, yeah, so we have a very similar example like in our introduction, but now we have kind of one time in the deterministic version in our f, and one time the same in our probabilistic version, yeah, and here it's just another constant now, a better, but still times u. And now our stochastic calculus tells us that the real solution is now represented as such, and you see already the big change. So instead of only depending on the time, we also depend on the random value, yeah, on the randomness at the current time. And given this, we can now specify what the system does. So we can also put this into Julia. So you see it's really identical. So this is just one of the standard ways to define some differential equations which is supported. And now we use SDE instead. Yeah, so stochastic differential equation problem instead of an ODE problem. So in this way we already have the support and can use the same idea. And I now need to switch to my other tab because my kernel broke down on the original notebook. So I can execute this, and I can see that the system also works. So I get my problem description, and I can also solve it again and plot the solution. And here there's kind of one standard solver which is used quite a lot, the Euler-Maruyama algorithm. So I'm actually not sure whether I pronounced that right. Still, it's kind of standard. If you have a different description of your problem, you need a different solver for it. It's just kind of the usual thing. From an outer perspective, it looks a bit like everything is the same, just adding a bit here and there, but these are quite different problems, and you really need to tweak it to get it performant and to solve it. So you can imagine that for everything there is kind of a generic solver, but it would just take too long, yeah. And here it's really, in this differential equation system, it's really knowing your problem well and choosing the right solver for your problem. And here we actually, for this solver, we need to provide an additional argument, the time step, which we want to solve. And yeah, so we can use Plotly to have nice plots. There's some section, I think we need to skip it. 15 minutes left for our 1.5 hour slot, but we want to have some time for further questions. So we have kind of ways to improve here. So this is just adding the analytical solution to the system and plotting it, and now using another solver. Yeah, so that's kind of what happens in this section. Instead of using the Euler-Maruyama solver, we have another solver which actually has more accuracy because it provides a higher order approximation. And yeah, with this little extra here, the plot analytic, we then get from the plot support to actually have both our approximation and the analytic solution. So again, first time we load the plots takes a bit longer. I really hope that in future versions of Julia this is much faster, also by default, and they're working on it. But still, so now if we restart the kernel, we still have this little overhead that the first time the plots library takes a bit longer to load. So what I really would like to show you is that differential equations comes with an ensemble support, which is super nice for the stochastic stuff. Because with randomness, not everything is the same. If you do one trial, it looks different than the second time. And yeah, and this is a super nice use case to actually try it a couple of times. And we can do it by putting our problem into a wrapper problem, which is here an ensemble problem. And with this we get support for multiple tries. So we can now solve our ensemble problem, and yeah, we can actually solve it on multiple cores, multiple machines. Julia comes with excellent support for distributing computations over large clusters. Here we only have a single machine, so no way to showcase a large cluster with binder, but that's fine. We have an extra support for multi-threading, so which just uses a single machine but still can parallelize and speed up things a little bit by using threads. And you activate this by using the ensemble threads. Yeah, it's like a marker here from the API call. And yeah, so now I have a couple of plots, so this took quite a while. I'm sorry for the delay, but bear with me. So if we have the first plot, yeah, we've solved our stochastic system. Thing to try out to really plot it twice, and you see it's really different. Yeah, so this is random. There's some randomness involved, and yeah, so this is key. Still, we can kind of look at it and see how good it is compared to our analytic solution. That's nice, and we see that if we change the solver to this apparently better one, we really also see that it provides a better approximation. So that was this section about it, to give you a feeling, okay, even in such things, the solver is quite an important choice. Of course, it takes more time. And here we have now our ensemble, and we solve it again and just let it run a couple of times. And yeah, and we can't plot it directly, of course, because there are now 1,000 directories, 1,000 trajectories in it. Instead, we can use some support for ensemble analysis, and this is really nice to show. So there's a special ensemble summary, which will give us, which has a couple of extra options, but most importantly gives us the quantiles. And by default, you see from the title here, it provides the 95% quantile, and we can also provide them on our own. And here we again use first the plot and then the plot with an exclamation mark to override our system, our current plot. And this is really a nice little plotting of the system. And of course you can have it with a more complicated system. This is now the example taken from the documentation of differential equations. And yeah, so it's just a linear line, but still you see kind of the quantiles, and you can easily imagine that this now can get complicated plots. You have also some functions to get some statistics about it, so a time point, mean, correlation, covariance, a lot of things. Take a look at the documentation. You have also a time series version of it where you can provide not only time points but a whole vector of stuff. So there are just some convenience functions to investigate these example problems, and in this case the example solutions. So also when I tested it before, this took a bit longer. On my local system it executes rather fast, but yeah, because we have a relatively slow or not so powerful instance at our fingertips, doing the same thing 1,000 times is already taking a bit longer, I guess. So again, with Julia, these things are optimized in the sense that the first run does pre-compilations, so that then the consecutive, the other 999 runs are much faster. So this, in the sense, kind of a good task also for Julia to do things again and again, because there the performance improvement can be shown. Still a pity that the plotting is now not super interactive here, but I will come back to it. So I think this is actually, yeah, we have kind of two examples in this section which I took over, and I think the second example is just nice to go into, because we saw also this example on the deterministic version and the ordinary differential equation setting. So this is again our Lorentz attractor now, but with some randomness involved. So we again have our general random modeling of a stochastic differential equation, and what is now modeled here is that we again have our Lorentz attractor with the standard parameters, so not parameterized but hard-coded, and we give a constant randomness. So we say that our random part here is actually a constant vector of 3 multiplied by our current randomness. So what you would expect is really just a noisy Lorentz attractor. And this is actually what happens. So it just adds some randomness on top of the Lorentz attractor. And we again use our 3D plotting here, but now only run it from 0 to 10. Remember, back then we run it from 0 to 100. Now to just visualize the randomness a bit more direct, 0 to 10 is just nice. And yeah, and we can also get things out of hand. So this is just another noise function, overwriting the function with a different implementation. This actually is just showcasing that you can do it, but the result is not interpretable. Yeah, so this just explodes, and actually the times I tried it, it literally exploded, because then values got out of range and the accuracy was no longer guaranteed. So we get an error message that this thing is actually unstable. And yeah, so I think that's nice. That's it. Let's hope that we get we have the plot over here. So this is the ensemble simulation, which I really wanted to show you that you can do this. You cannot only do this with stochastic stuff, but of course you can also do this with a series of differential equations you want to solve. So, but for the stochastics applications, it's really natural because you want to see what does my system do on average, and what is kind of the error bars which I have. And here it's quite a linear system, not so interesting, but you can make it complex as you like. Still, you see that we have actually a systematic development of our final function. So in the beginning it just looked random, and now we kind of get out the randomness and really see that there is this linear relationship here, which then is exponential. Okay, so this example is still computing. Okay, so last example which I put here is just to showcase, so this actually doesn't execute, it just gives an introduction that you can use other randomness in the background. And the simple example here is that they have a correlated Gaussian process where two Gaussian variables are actually correlated. So we have kind of a differential equation, a stochastic differential equation system with a dt and a dw. Yeah? But in addition, we have a dw1, dw2 is defined as some constant rho. So that's kind of our interdependency in our randomness process, in our noise process behind the scene. And this is called a colored noise, so that we don't have a simple diagonal Gaussian process, a diagonal Wiener process, but a more complex one. In this case, with we define the covariance matrix, the correlation matrix, and can construct a correlated Wiener process. So the Wiener is really the W, and yeah, get the same thing running. And you have a lot of other processes there. And yeah, the last hint here is that actually this example has more support. So this is a well-known in financial applications. It's the Heston problem. I haven't worked with it in my study. I was more on the math side of things, but still nice to see that these financial models are supported also here and have the modeling toolkit. So we saw it in the general section. Yeah, so we have this financial models here, and we can see that some of them are directly supported, so that you just can be sure things are right. I'm not so sure about the community around this, how large the financial community evolved already in the Julia ecosystem. Would be nice to know if someone is in there. I think the application is quite obvious. So now we have the randomness. The first Lorentz attractor already is plotted. So we have a nice 3D plot of our noisy Lorentz attractor. The first from 0 to time 10. You can play with it a bit longer, and the other one already also gave the error message, so it's aborting. So there's either an error in your model specification or the true solution is unstable. And yeah, and we see some weird stuff happening. Yeah, so that's just illustrating that this is possible. Or we may actually zoom into this field here in front. So it could be nice. Okay. 3D zooming is not so simple apparently. Okay, yeah. I can't see a pattern. Great. So the last thing I want to show here to summarize as well, and then we also hit the 1.5 hours, is that especially in this randomness part, which I especially like, there is another set of random functions. There's also another tutorial for it. It's called the random ordinary differential equations. They are defined a little bit differently than stochastic ordinary differential equations, and we can put this nicely into formulas. And the way now is that the random process is just an additional parameter. And this representation is apparently more powerful than the other one, but on the other hand, you also need other solvers to solve then these systems. So there are some examples here also what you can do with that. But I think it's just nice already to just see that you can define random processes also in a different way by providing it just here as a direct parameter. Maybe more intuitive to start with, because then you just play with it like a normal variable. You don't have to worry so much about what it means to have this dw here in the back. Maybe a bit more intuitive. Okay, so thank you a lot for joining today's introduction into the differential equations package ecosystem. Check out the tutorial, check out the these tutorials here, the collection of tutorials. The documentation has a lot of more stuff in it, and also check YouTube. There are many things over there, and the standard Julia teaching material is also kind of your friend. So if you don't know this page, that's the way to go. Next, download Julia, just try it out. And here at the top, you have also the Learn tab, and under Learn you have a lot of resources to continue also with differential equations, but anything in the Julia ecosystem. So there's really a lot of material you can check out and use. Great, little check over the questions. So we have Chris answering a lot of questions. Thank you so much, Chris, for joining here. So we have some input on the testing part of it. Very important to get things right. In academia, maybe not so much, but in production setting, it's just it's needed, it's essential to do the testing right, to have a feeling what the system does. And yeah, also for debugging. Thank you, Krishna, also again for answering. Yeah, this reminds me also of one application. So you check also out neural differential equations. I definitely will do an introduction to that one too. Okay, quite a lot of input. I'm just skimming over it. Thank Krishna and Christoph for all the input. I will check it out in a second. Just seeing whether there are some further questions. Okay, so great. Seems maybe I missed a question. If someone had put a question there, just repeat it for me. Thank you all then for joining. We have a bit more time probably for questions. Feel free to ask if Christoph or Krishna are going to stay a bit longer. That's also kind of super valuable. I'm also staying a bit longer. I can give you anything any hints about how to start with Julia, what are kind of also pitfalls there. If you're interested in the general stuff, also feel free to ask. Then I have to say thank you for joining today. It was a pleasure having so many people joining here. We can stay together and sync each other via the meetup. We have Julia is also connected via Tulip, via Slack as well. Christopher just put the Julia Slack channel. We have also a Tulip version of it. You can also find it linked on the meetup page. Yep. Thanks for joining. Have a nice evening, everyone, and feel free to just stay a bit longer and ask whatever you have a question.